Good afternoon, everyone. Welcome back to E304. In this lecture, we're going to talk about some of the applications of the oscillations and vibrations that we've been discussing over the past few lectures. So in this first application that we're going to look at is a nanomechanical memory system. So let's imagine that we have some beams that are connected or fixed on both ends. So we have three beams here, beam 1, beam 2, and beam 3. And you can see that they're fixed on both ends. And some driving force is applied to them. And you can imagine this as a string on a violin. You know, it's attached on both ends, and we draw the bow across it, and you cause a vibration in the string. Well, these beams are a little more interesting, I think, than the traditional violin strings, in that they have this bistable mode where they can exist if the driving force is FB is at the proper frequency. The system can vibrate with either amplitude 1, high amplitude, or amplitude 0, a low amplitude. So at the same driving frequency, the amplitude of oscillation can be either a high one or a low. Okay? And the way that you can get the system to switch between oscillating at the high amplitude versus the low amplitude is with an external force like an electrical current. Okay, so if we drive the system at the proper frequency, we'll call that FB, so that you're in between these two, right in the middle of this bistable region. Then by applying the right electrical current, we can get these to oscillate at the different amplitudes. And if we consider the high amplitude a logic 1 and the low amplitude a logic 0, we can encode binary code using these beams. So with three beams, you can encode a logic 101. Okay. The next application that we're going to look at is in mass sensors. So in this case, we have a beam that oscillates. So the beam is attached on one end and free on the other end to oscillate. Well, we know that the natural oscillating frequency for a system like this depends on the spring constant, K. It also depends on the mass of the beam. Well, if this beam comes in contact with some molecules, and those molecules absorb or attach themselves to the surface of the beam, then that can change the net mass of the beam. And if we change the net mass of the beam, we change the resonant frequency with which it oscillates. So if we see this frequency shift, we can detect that some mass was absorbed to the beam. So this is useful for mass sensing. The other quite popular application of the cantilever or the beam is in scanning probe microscopy. So this is STM and AFM, and I'm going to post this video as well that you guys can look at on your own time. But the general process by which we do scanning probe microscopy is shown here. So in essence, you have a cantilever or a beam that's attached at one end and free on the other. And at the tip of that beam, we have a very sharp stylus or tip. Okay, and this is a sub-nanometer, very, very, very sharp. So as we drag this probe across our surface of interest, it'll bounce up and down. It'll vibrate and oscillate, right? And if we shine a laser towards the tip of that cantilever, and we look at the reflection of that laser beam, that reflected beam is the angle of reflection is going to change based on the angle of this beam. So if it's deflected up or down, we're going to be able to tell that with the laser. Also, we can use some piezoelectrics to detect the motion of the cantilever based on its bending force here. And also we have some feedback loop usually that goes back from the detector and helps us maintain a constant force or a constant amplitude of oscillation here. So let's look a little bit more detail at the STM. So the scanning tunneling microscope, this was first developed in 1981, and the folks who did it got a Nobel Prize for it in 1986. This has a very good resolution, about 0.1 nanometers laterally and 0.01 nanometers in depth. Now let's see how it works. So the scanning tunneling microscope, and the key word here is tunneling, the key process by which this works is that there's atoms on the surface that you're looking at, and then there's atoms that make up the tip of your stylus or your probe. And although the stylus in this case doesn't actually come into immediate contact with the surface, if it's brought close enough together, this atom can tunnel. So there's an electromechanical interaction between the tip of the stylus and this atom, and the atom can sort of be picked up and moved by the stylus and then dropped someplace else. So by this method we can sort of push and move atoms around at the atomic level, which is it's quite neat. The other type of this type of microscopy is atomic force microscopy, or AFM. And it's a very similar setup. It still has a cantilever and a probe tip. And you have a sample, but in this case you're actually dragging the tip across your sample. And you can do this in a number of ways. You can either maintain a constant force of your tip to your sample and scan across and measure the deflection of the cantilever, or you can use this sort of mechanism in what they call tapping mode. And that means that you keep the cantilever oscillating at or near its natural frequency with a constant amplitude, and sort of tap along the surface of your specimen as you go. And this is better for soft samples, and you're measuring force in that case. So this is, again, these sorts of things always have a feedback loop that either maintain a constant force or they maintain a constant amplitude in order to get the measurement that they need.